Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module experimental techniques from the paper Solid State Physics. So students, let's see what we are going to learn in this module. So we shall talk about or learn about X-ray diffraction techniques, different X-ray diffraction techniques, and we will learn that how these techniques are used on a specific type of a sample. You know that first how this idea came to Love. He was in his laboratory and doing an experiment of diffraction grating. So that was an experiment with a visible light, and as you know, when you put a diffraction grating, you obtain a diffraction pattern. So this is diffraction grating is basically a film where you have a opaque and transparent, opaque, transparent, this kind of lines in a series, and or you can say these are the planes through which light can pass, or from the opaque region light cannot pass. So he correlated that the wavelength of the visible light is of the order of separation between these two fringes, to opaque part or to a part in which the light can transmit. So he had an idea that if we can have some radiation where its wavelength is of the same size as the atomic planes or interatomic distances, then we can basically see the X-ray diffraction pattern. So it took a long time uh, afterwards, though, to brag and uh, to really see the diffraction pattern. So in this chapter, we will discuss this X-ray diffraction techniques. One is this Lau method. In Lau method, we will discuss in reflection geometry as well as in transmission geometry. We will see the Lau pattern, and then another method which is called rotating crystal method, and we will also talk about Evaldi sphere in this, and the last one, which is very popular X-ray diffraction techniques and in all found in almost every laboratory, is a powder diffraction method. X-ray diffraction techniques, let me have you an introduction of this techniques, because as we know that in laboratory, when we come with certain specimen, right now first of all we do not know whether this is a crystalline, this is amorphous, or it's a polycrystalline or a single crystal. So depending on the need, you need different experimental methods which are convenient for particular type of specimen. So in this case, usually when we have a single crystal and our X-ray source is not monochromatic and it's a polychromatic, so we can use this Lau diffraction method, and that we can use in transmission geometry as well as in reflection geometry. And to find out the orientation of a crystal, let us say if you are handed a piece of crystal in the lab, just by looking at it you cannot know which is the A axis, B axis or C axis in the crystal, even if it is a single crystal. So you need to mount it on a diffractometer and you need to found its direction or orientation of axis. So that is done by rotating crystal method. And in third type, which is very convenient, is powder diffraction method. I mean, you can have a polycrystalline sample, you can powder it nicely, finely, and so that all orientations of crystal are available, and you can mount it on a goniometer. In the source is usually monochromatic, actually monochromatic in this case, and you can vary the angle theta, or you can use 2D detector even. So we are going to uh, discuss these techniques in details in the coming slides. X-ray diffraction techniques. So when we talk about X-ray diffraction, there are several methods and several ways in which an X-ray diffraction experiment can be performed, but these are uh, these three which you see on this slide are quite popular techniques and known as a technique. So we have just shown them as a three different techniques of popular type. So you see that there is a law of diffraction, and it's written orientation single crystal, polychromatic beam and fixed angle. So that is generally the geometry or characteristic of this Lau pattern, that we take an X-ray beam which is not monochromatic. It has a range of wavelength, and we put a crystal, a single crystal usually at some orientation, and we obtain a diffraction pattern on some plate, and from there we try to find out what is the orientation of the crystal. And this next technique is written as rotating crystal method. So in this we would like to find out the lattice constant, and usually we work with the single crystal systems, and here the beam is monochromatic and angle is variable. So we already choose some particular wavelength, but here the angle of a crystal can be varied and changed in a different way. And the third one is a powder diffraction technique, and this is the most popular in X-ray laboratories. You see in any university setups and all, this powder X-ray diffraction pattern is what is easily available everywhere. So what we want to learn from this is lattice parameters, and here we use a powder sample, polycrystalline sample, and we use monochromatic beam and variable angle here. So this is how I have just classified, or just these three techniques I have written on this slide. But as I told you, there can be many ways or many other techniques for doing diffraction experiment. Lau method. So the Lau method is mainly used to determine the orientation of a single crystal while radiation is reflected or transmitted through a fixed crystal. So we have to take up a crystal which can be thin, because we can do this experiment in reflection geometry as well as in transmitted geometry. I mean, we can study reflected beam as well as transmitted beam and see what kind of pattern they form. The diffraction beams form arrays of spots that lie on the curves on the film. As you can see uh, on the right hand side, this is a diagram. This is a particular uh, X-ray diffraction, a Lau pattern, so to say, of a given crystal. So the Bragg angle is fixed for every set of planes in the crystal. Each set of plane picks out and diffract the particular wavelength from the white radiation that satisfy the Bragg law for the values of d and theta. So in the Lau pattern here, uh, what we're doing in earlier diffraction techniques, as we discussed, that we vary the angle. Here we don't vary the angle, but we have, just because this polychromatic beam with us, so due to that factor, several different values of d can be correlated, and you can get a diffraction pattern uh, immediately from this technique. Okay, so as you have seen that in Lau diffraction pattern, in Lau diffraction experiment, which is rather simple in its geometry, because what you need is an X-ray beam which can be polychromatic, and you put a sample in the beam and you see the geometry either in reflection or transmitted intensity. In this figure you can see the transmitted intensity, and you can see there is a plate, what we call a photographic plate, placed uh, in the beam, and there are some spots. You can see that they are lying in a circle. So these diffraction spots here, they are actually map of reciprocal space, or in other words we can say that they satisfy Bragg diffraction condition or law of diffraction condition. So apparently Bragg diffraction condition 2d sine theta is equal to n lambda and law condition delta k is equal to g, they appears different but they are same, and you can derive a mathematical relation to show that basically these are equivalent or two different statements of the same thing. So this is basically the geometry of Lau diffraction experiment, from where we can identify the symmetry of the crystal. And you can see that one side of cone of Lau reflection is defined by this transmitted beam after the sample, and the film intersects this cone, and you can see the dots uh, at the circumference of the circle. Okay, so this powder diffraction method is used to determine the value of lattice parameters accurately. Lattice parameters are magnitude uh, um, of the unit vectors A, B, C, which define the unit cell of the structure of crystal. For every set of crystal planes, by chance one or more crystals will be in the correct orientation to give the correct Bragg angle to satisfy Bragg equation. Every crystal plane is thus capable of diffraction. Each diffraction line is made up of a large number of small spots from each separate crystal. Each spot is so small to give the appearance of a continuous line. So that is what happens in powdered X-ray diffraction. So in a powder you have so many large crystallites that uh, all all crystalline planes are basically accessible to us in this pattern, Lau pattern. So this is another example of a Lau diffraction pattern where we have performed this experiment in a transmission geometry, and this pattern is perpendicular to the direction of X-ray beams. So you can see there are some spots which are arranged in some particular nice way, and this arrangement of these spots is basically a representation of a reciprocal space. We have already learned about reciprocal space, and that is a direct vision of this reciprocal space of a particular sample. This pattern also reflects the particular symmetry of a crystal. For example, if it's simple cubic or if it is a hexagonal symmetry, depending on that we will obtain this pattern, and from this pattern we can identify what kind of symmetry this sample will be having. Now you can see that there are dots at a large distance, and on the opposite side you can see the horizontal line of spots and vertical line of spots in this diagram, and these spots at the large distance, they reflect the spacing uh, of atoms at the smaller length scale, and you see that near the center you have several spots. So these corresponds to the small length scale in reciprocal space, but this corresponds to a large length scale in the real space. So in real space at the large scale there is some another symmetry which is coming up, which is not there at the small length scale. So basically this is this diagram is a real space mapping of that crystal what you have, and the idea is that once you have this reciprocal space mapping, you can convert it into a real space mapping by doing Fourier transformations of this kind of pattern. Rotating crystal method. So this slide shows us the geometry of the rotating crystal method. In rotating crystal method, a single crystal is mounted with an axis normal to a monochromatic X-ray beam. A cylindrical film is placed around it, and the crystal is rotated about the chosen axis. As the crystal rotates, sets of lattice planes will at some point make the correct Bragg angle for monochromatic incident beam, and at that point a diffracted beam will be formed. So in this diagram, as you can see, that there is an X-ray source and incident beam which is coming, and it is passing through some sample in the center, and this cylindrical thing which you see, this is a circular film on which a diffraction pattern is recorded. You can see these spots. So these spots are diffraction pattern coming from a sample which is in the center of this diagram. So whenever this Bragg condition is satisfied, you get a spot. So at a particular angle, this Bragg condition is satisfied, and you instantly get the information of the reciprocal space of the sample. Now we show here you the equivalence of Bragg condition and the Bragg condition and Lau condition in terms of Ewald sphere. So you can see that this diagram which is shown here in terms of dots, this is not a real space lattice, but this is a lattice, reciprocal space lattice. Now we already know the wave vector of an incident wave, and the wave direction of wave vector is always in the direction of incident X-ray. And so because we know the length of a vector, we can draw a vector, and then also a scattered ray, you can plot it like this, and you see, so k minus k dash delta k, it will be a wave vector transfer, and if this wave vector transfer is equal to some reciprocal lattice as this shown in the diagram, that's this difference between k1 or k incident to k minus comes out to be equal to the length of the reciprocal lattice, and that means the reflection condition is satisfied, and that means that this point now will lie on the surface of the sphere. I mean, you take this point as a circumference or the outer surface of the sphere, and from the center you can draw the sphere, and then whatever sphere you get is a Ewald sphere. So the point is, any point which is lying on this Ewald sphere will give you will satisfy the Bragg condition or Lau condition, or will result in the particular reflection for that given direction. So this slide shows us that how can we determine the lattice constant by rotating crystal method. So you see the formula here, d is equal to a upon under root h square plus k square plus l square. So from a given value of theta, from the Bragg relation, we calculate the value of d, and when using this value of hkl, let us say 001, we find out the value of the lattice constants. So first we have to identify that which HKL plane this peak belongs to, and put the value of HKL, and we know D we have already calculated, so we can here find out the value of A, the lattice constants. So with the rotating crystal method, the idea can be extended. Just from calculating the lattice constants, we can find out the shape, the size of the unit cell, and the orientation. The question here is that if you are given a crystal and just by looking at it, you cannot locate which is x-axis, which is y, which is z-axis, or what orientation this crystal have. So the best way is put it in X-ray and rotate it, and for a given angle record the spectrum, and that spectrum will help us understand that along which axis you have a larger unit cell, a larger lattice constants, along which direction you have a smaller lattice constants, or in a way you can identify the symmetry of this crystalline structure using rotating crystal method. So the diffraction for a film is shown here. You can see the white spot, this is the direction of beam, and this black spots are the diffraction spot for a particular orientation. So now when you will orient the crystal in different way, you will get this diffraction pattern in a different way. Powder diffraction method. So this is the third method which I started with, and this is probably the most popular method in X-ray diffraction used, which is called powder diffraction method. So what is the meaning of the powder here? As you can see in the diagram on the right hand side, there are some crystallites which are there inside the circle. So these are crystals which have different orientations. So here powder basically means that the crystal system, the piece of crystal system which is under examination, which we are examining, is not entirely a single crystalline piece, but basically this is a set of different crystallites and they are oriented in different direction. So usually when we talk about crystalline materials, they are polycrystalline in nature, and that is what it means by polycrystalline, that they are powder in the form. They have small crystallites will have different orientation. A single crystal uh, would in a single piece can be defined with a single set of axes, and using the single translation vector one can go from one atom to another. But in polycrystalline sample, that translation symmetry is broken at the grain boundary. We cannot go there. So that is what it means. Though the sample, all crystals are made of same samples, but they have different orientation. So when you put, you can see that a powdered sample in a X-ray beam, an incident X-ray beam. So different d spacings are available to you, and at a given angle theta, at a particular angle, this spacings will diffract, and you will uh, obtain the information of this different planes by scanning the angle theta. So you put a sample and scan the sample theta. So in a slide 15, so in this slide you can see that these are the typical samples or powders which are used for powder diffraction patterns. You can have a little crucible and you can just grind your samples here. So here grinding means you are breaking them into a fine crystallites. They are still crystallites. Any powder which you see, they are of the order of some hundreds of micron size of grains, and but they are all crystallites, and you paste them on some slide and you make the measurement. So basically you get all the orientations of these crystals by making this powder, as you can see. And now for you, all the planes will be accessible when you rotate the angle theta. In case of single crystal, this is not possible. So students, let us summarize what we have learned in this module. X-ray diffraction is a non-destructive technique. Some of the uses of X-ray diffractions are um, differentiation uh, between crystalline and the amorphous materials. So I use the word here non-destructive. So non-destructive here means that when you expose the sample to the X-rays, it does not do any harm to the sample, but in certain cases it does if the sample is organic. So usually with the inorganic hard samples there is no harm, and we can understand if the sample is crystalline or amorphous just by if we are getting the diffraction peak or not. Then we determine the structure of the crystalline materials. First we knew that it is crystalline. Now we can find out which class of crystals it belongs to, which kind of symmetry it belongs to. And uh, we can also, the determination of electron distribution within the atoms and throughout the unit cell, that is also possible by fitting of this atomic form factor. We learned about atomic form factor, so through that we can also learn electronic distribution in atoms and molecules. And determination of the orientation of a single crystal. We can find out the orientation of a single crystal given to us, and we can determine the texture of polygrained materials, and we can also measure the strain in the samples and a small grain size, etc. So how to measure the strain? As you can see that if there is a certain interstitial vacancy and this causes a strain and at that location, or the plane can be slightly tilted, so that will cause a shape change in your diffraction peaks, and your peaks are not symmetric. So from the asymmetry you understand that in particular family of plane there is some distortion, strain, and so also you can find out the size of the grain, because the crystallite size are sometimes very small, of the order of nanometer. So then you can see that the constructive interference is not perfect in that case, and there is a broadening of the peak, and from there you can find out the size of small grains. Thank you.